All right, thanks everyone for coming. I'm Sarah Christoph, like he just said. And if you still don't know who I am, then don't worry about it. Just know that I am an apprentice engineer on Consul, and my mom does say I am cool. So usually in my talks, I try to make an agenda or a lesson plan. We start with building the base, the sides, and then the summary is always a roof, like a house. This talk is a little bit more complex. We're going to go over Consul's history, why it exists, the problems that came across when building it, and basically what has become today now Consul. So we're going to start with the problem. Why did we build Consul? Go over things like swim, memberless, surf. You've probably never heard of them, neither have I. And eventually we'll end up knowing more about Consul in the end. So what was the problem? Right? I used to work as a systems engineer at a consultant firm, and I've worked with really large enterprises, not to try and humble brag. If you work at a large enterprise, you know it's not great. So I was used to hard coding IP addresses everywhere, even though we were in the cloud. And I figured this was a problem, and even though I wasn't technically apt enough to solve it, I just whined about it. Well, guess what? Armon probably had that same problem at least once, and I think he did something about it, maybe. And if you don't know who Armon and Mitchell are, then they were literally the people here yesterday, and they're our co-founders and CTOs. So to fix the hard-coded IP problem, we had to figure out kind of a model in which we wanted to tackle this problem. We tried to find the most fault-tolerant, robust, scalable solution. When I say scalable, at the time, what I hear was scalable was 5,000 nodes. But we wanted something hip, something cool, you know, like me. So what we originally found out is something decentralized because it's scalable, and it's very easy to reason about, and it's very fault-tolerant. Fun fact, in the 1990s, when things like ARPANET were floating around, might be a little too late for ARPANET, but the internet was made to be decentralized because the internet was made for the military to use to communicate. So to cover what centralized and decentralized is, centralized is when all of these nodes go to one point for their information. Decentralized is when we have those basically key nodes, multiple of them, and we can go to different points for this information. I like to think about it, I've worked at a WordPress hosting site before, and so I like to think of them as MySQL databases. So you can have one MySQL database and everyone hitting that one MySQL database, or you can have many of them and us all hit those many different points. So admittedly, I played Destiny 2 very poorly. So this is what came to mind when I heard peer-to-peer. Peer-to-peer is used a lot in online gamings, and it's actually more cost-effective for companies to use the peer-to-peer model because they get to offload the cost of having your dedicated servers. Well, they offload it on the users. So in my Destiny model, basically, when I join an online match, then someone in that match becomes the host. The rest of us are clients. Every shot, kill, movement is registered through that host. It's checked, and that's where it's stored. If that host has poor internet connection, if they drop out, things like that, that's going to affect your gameplay. Hopefully it doesn't, but you're all huddled around this one person, praying that they have good internet connection. That also leads some vulnerabilities. If I'm the host, then I can say I killed 4 bajillion people and I'm the best Destiny player. And you know, that can maybe upset some people. So in cases of like Counter-Strike, which use the dedicated servers, every shot, kill, movement it goes through those servers to basically check the validity of what you're doing. So from here on out, it's best to understand that peer-to-peer is decentralized implicitly. So now we know what decentralized peer-to-peer communication is. What do we do with this? We still, you know, have this problem of hard coding IP addresses everywhere. Well, after evaluating a lot of protocols, we decided that gossip was scalable, efficient, and you'll see this a reoccurring thing, simple. Maybe some would say not simple, but it was time to start researching how we would implement such a solution. And so that's where gossip protocols came into play. To explain how gossip works, I found this story that my significant other told me the other day. He said, in the military, if you're in the mess hall and you drop one of the glasses, that person has to say, broken glass, be careful. Everyone around that person who hears that phrase has to then repeat it. And that goes on and on and on until everyone in the mess hall knows that there's broken glass, be careful. And he says, if there aren't walls, if there were, say you're in an open field and you drop a glass, then everyone in that open field would know, hey, someone dropped that glass. So you can see that gossip, it uses the same method of spreading information from one node to another, to another, to another, picking up traction as more people hear this information. And if you don't believe that this is a good model, you should go to high schools, because rumors do spread. So there's two different primary types of gossip protocols, and we'll go over a couple key distinctions in different types of gossip protocols you can choose. One is structured versus unstructured. So in structured protocols, you're looking at rings, binary trees. The trade-off here is they're more complex. When they try to fail over or recover from a failure, then it can be more complex to reason about, or it couldn't just happen at all. If the structure is broken, it just can break. Unstructured, being things like epidemic broadcasts, like we just talked about, are simpler, they're more failure resistant, but they're also slower. Cool. So another important consideration was taken about visibility. So a question I asked was basically like, for gossip protocols, why don't we just have the gossip protocol just only talk to who's close to it? Just know those people, and there you go. And eventually, like, if you take that model and you scale it, those people would only talk to the people close to it, and so forth, so we'd have overlapping kind of members. The reason we didn't choose this is because limited visibility, again, increases the complexity, and even though it could increase efficiency, but it opens doors to failures not being recoverable as fast. So there's lots of trade-offs, as you can see. However, full visibility, it's simple. We know everyone knows everyone. And with that, we have lower complexity. So now we have all these ingredients. We know we want gossip because it's peer-to-peer. We want something unstructured because we want to have something randomized and something based off of epidemics. And full visibility, because basically our goal here is to keep it simple. And that brings us to Swim, our flavor of gossip we decided upon. Now we're going to talk about some of Swim's features and break down each of the words that make up Swim. That's because every website about Swim does this. So first we're going to talk about scalable. If you guys work in the cloud, or I assume you do because you're at HashiCorp, you should know what scalable means. But originally, the Swim paper only talked about, I think, 50 or 60 nodes. It was written in 2001. So when we were looking at it, like I told you, we were hoping to scale up to 5,000. That was kind of our cap. We were like, that's a huge cluster. And this scalability extends to how all of the features around how it's built. Weakly consistent is a really fun one for me because as I wanted to explain about consistency models, I found that not only are there 50 plus consistency models, there's a lot of inconsistency about consistency models, which is fun to say. So Swim is weakly consistent. And that means basically it can take some time to get the information you want once you send it up into that node. Now, eventually, it'll resolve. But sometimes if, say, I send my information up to node A, and I say, hey, key equals 1, and node A explodes, then guess what? That's gone. There is no guarantee once you send up that request to node A that it will be stored. And in things like databases, that's a pretty big deal. So this will eventually converge, typically in about 2 seconds, but it's not immediate. And the swim paper touches on why they did this. The TLDR is, again, the stronger the complexity, or the stronger the consistency we add, the more complex we get. And like I said, again, lots of trade-offs. And then infection style process group. This is our snazzy way of saying that this is a gossip or epidemic style broadcast, to broadcast information. And membership. Well, it seeks out to answer the question, who are my members? So some of the really cool properties of Swim are around its scalability and failure detection. So in Swim, no matter how large the group size is, the load per member stays about the same, and that's regardless of cluster size, because basically, no matter how big I get, I'm only going to be sending out my pings and ACKs at the same intervals. We'll cover more about that later. For failure detection latency, this is also independent of the entire size of the cluster. And we'll cover more about failure detection in a second, but our rate of announcing that we have a failure always stays the same. And we use Gossip to send out membership updates, alive, suspect, and dead, throughout the cluster. So one of the key requirements was we needed to understand node failure in order to move faulty nodes from the group, right? You'll see here that I put not heartbeat driven. And that's a big deal because heartbeats is basically, I am a centralized node and I send out, hey, are you alive to all of the nodes in my cluster at a regular rate? Now, this can increase complexity and also increase resource utilization. So we needed a different approach from other protocols. And when we cover the failure detection, this might actually teach you a lot more about how the protocol itself works too. So in this scenario, we're sending out a direct probe to node B. We're saying, hey, are you alive? How are you doing? We expect to send this node out and get a direct probe back that says, hey, I'm alive and I'm doing well. Typically, we have lots of friends in the cluster to make sure that this one node is alive. But if node B doesn't respond, what do? We can ask another node to probe node B on our behalf. This is called an indirect probe. We'll message node C and say, hey, my friend, I can't hear from B. Can you talk to him for me? Maybe node B's mad at me. If node B responds to C, and then C will say, hey, I heard from node B, and maybe node B will ask us if we're OK. But let's say, hey, no one can hear from node B. What do? We start telling everyone, hey, I can't hear from node B. This is a big deal. Eventually, there will be a timeout reach that says, node B's failed. We're not going to talk to node B anymore. They're not cool. So one of the biggest properties of Swim that we'll iterate on is the incarnation number. The incarnation number is stored locally on the node. And it's basically to help us refute false suspicions. So if I'm node B and I know I'm alive and someone tells me I'm dead, I'm going to say, I am not. And so basically, if I get that, if that does occur, then I will increase my incarnation number to say, hey, I'm alive, someone said I was dead. Cool. So now we know more about Swim. And Swim is like our recipe. We take sugar, we take some spice, we take some robust failure detection, and we make a slide. Sick. And we make member list. So up there at the very top, that's not highlighted anymore, that's a quote from Armand basically saying, member list was supposed to be our purest implementation of Swim. Now, Swim, you can see here, is Buttercup because, or member list is Buttercup because member list is strong, and for some reason, grumpy. So member list gives us the 3 states again from Swim, alive, suspect, and dead. We have indirect and direct probes for liveness, and member updates like, hey, I think this guy is dead, or hey, I have joined the cluster, will piggyback off of those probes. We added a bunch of additions to member list, or to swim in member list. One of them was using TCP. So in the original swim papers, we only used UDP, but for member list, we added TCP to send direct probes in case there might be an issue with traffic or network configuration. So say you don't have your UDP port open, then guess what? This isn't going to work. So we use TCP just in case stuff like that happens. We also added an anti-entropy mechanism, which basically helps us sync state between nodes. So randomly, I'll choose a node in the cluster and say, hey, let's meet up, let's talk about all the things that's been happening lately. And so those state syncs will happen to help us converge on information. And then we also added a separate messaging layer for member updates. So basically, instead of just only sending member updates via direct and indirect probes, we separated that layer out because we realized it's super important to share that anytime anyone joins or leaves or dies. So on top of all of this, eventually, our research department and friends did research on how to improve member lists, and we came up with Lifeguard. We're going to touch on 3 key points of Lifeguard, and they're all there. I don't like saying the long words, so we're only going to say the short words. First one is self-awareness. So an awareness score changes due to the outcome of indirect and indirect probes. If I ask for a liveness check and I don't receive a response in time, maybe I was too slow to process it, right? And so if that's the case, then I will get a timeout from that indirect or direct probe, and I will increase my awareness score. Or say if I suddenly receive a large number of liveness pings, maybe the cluster thinks I'm offline, and I probably shouldn't suspect other members if I'm appearing offline. So what self-awareness does is if we're not feeling confident in ourselves, if we're thinking we're having networking issues or resource constraints or from another application, don't worry. We'll take that into consideration. Our awareness score will increase, and when the awareness score increases, us sending out suspicions will decrease. That's a quote from my dog. So, dog pile. So basically what happens is for each node, there's a suspicion timeout set before we decide, like, OK, you're dead, you're out of the cluster. For new suspicions, ones we haven't heard before ever, the timeout will be the longest. We'll believe, since this is the first time that we've heard the suspicion, that it's not true. But once we keep hearing the suspicion, once people keep telling us, hey, node B's dead, then we're like, maybe node B is like actually dead. And that suspicion timeout will decrease, till eventually node B is dead. So Dogpile assists with messaging processing to remove failed nodes. So even if there's a time of like high resource utilization, we can still quickly remove any kind of failed node. And lastly, we'll cover buddy system. So this prioritizes sending out suspicions. Like we covered earlier, member updates usually piggyback off direct and indirect pings, and because of that, it might take some time to send out a suspicion. Well, now, this time, anytime we think there's a suspicion about a node, that gets prioritized. Top of the queue, we're sending it out. We're going to let that guy know, hey, we think you're dead. And that way he can refute it, or she, and let us know that they're alive. If you want to know more about Lifeguard, please go watch John Curry's talk. It is very cool. Last thing we'll cover, I should actually tell the story about this gift first. So I asked Finzi over there about key rings, and it was explained to me that a key ring is basically, imagine you do have a key ring and you put a bunch of keys on it and you slam it into a door until it gets in and it gets unlocked magically. That's how a key ring works. So that's my definition, that's your definition. So a key ring is used to encrypt communications between nodes. I like to think of it as a plain text file, and that's read, and then you encrypt all your information that way. So many keys can be stored to try and decrypt a message. Similarly, many keys can be used to encrypt a message. In member-list, fun fact, dropping them everywhere, member-list, you can have many keys, but only one key can encrypt a message, or not, yeah, in member-list. So yeah, in many keys, one key can encrypt a message, but many keys can decrypt a message. So fun facts for the day. This is my favorite. So eventually we had member-list, and we were like, this is dope, but like, what are we gonna do with this? We can't, no one wants this. So we needed to add some features to make it user-friendly. You'll see why I put that in quotes. And we added surf, not swim. Too many S's. And just for a recap, this is where we're at. So like halfway through-ish. Cool. So in Serf, we added new functions. Vivaldi, which we'll cover, Lamport clocks, and CLIs. This is really just good to show the difference between the two that was made. Lots more, too. Many new functions. This is also my favorite slide. So we added a bunch of cool things to Serf. One of them is graceful leave. So say I don't like node B, but node B is alive. Guess what? I can tell node B to get out, and it will do it gracefully. Snapshotting, you can save the state of a node. Network coordinates. This ties into Vivaldi, which is also very fun, and we'll cover it soon. Key manager, you can install and uninstall keys, and much, much more. Oh, like custom event propagation. So you can add events that piggyback onto messages sent within the cluster. And it can be like, hey, trigger a deploy, run a script, whatever. The only constraint is there is certain message sizes that you must adhere to within memberless and Serf. So it has to be pretty teeny tiny, but you can basically do custom event propagation throughout the cluster to trigger deploys or run a script or whatever. You can do it off of member status, or say I only want to run this on like member A. So lots of customization. And now Vivaldi. That's a real pic of Vivaldi, really cool. He looks smug. So Vivaldi calculates the round trip time between two nodes in the cluster, right? And we use all of this information, all these round trip times, to build kind of a matrix of like where we think the nodes are. And here's is it gonna play? Cool. I cut this, and so now you get to watch the whole thing. So Vivaldi in Serf uses network coordinates to basically map out where Vivaldi thinks all the nodes are. There's a lot of cool stuff of Vivaldi, and if you want to know more about it, Armon talked about it, and this is how I learned about it, so you should check it out. Armon gives really good talks, by the way. If no one's watched his talks, like, super dope. All right, Lamport clocks. This is how I feel every time I read a paper by Leslie Lamport. Leslie Lamport wrote Lamport clocks, which isn't that complicated, but it replaces incarnation numbers to keep all of our messages ordered. And the Lamport clocks we use in Serf are used for every message and every event. We use it just to keep the order of things. Where in memberless, like we discussed, it's only used basically for suspicions. It's a logical clock that's event-based, and it's local to your node. And we added a CLI. Real pick. Okay. So the problem with Serf is people struggled to reason about the eventual consistency, and people wanted a central UI and API. So how do we accomplish that? That's right, it's Raft time. So we added Raft into the mixture. Strong consistency and central servers allowed us to give the things people wanted to them, like a central UI and API. So let's deep dive, and by deep dive, I mean like 6 slides, into Raft. So the first question is, what is Raft, and what does Raft seek to solve? That's basically to solve this consensus problem. So say you have 5 children. I don't know why. And you are like, all right, kids, what's up? What's for dinner? Well, I don't know. I, as a person, can't ever make a decision, so I can't ever see 5 people trying to make a decision and all adhere to it. So I can basically say, if you ask all your children what they want for dinner, then you're not going to get a decision. They will never reach a consensus. But Raft, if you used Raft on your children, I don't know how you'd install that, they would come to a consensus. So in the beginning, Raft has to decide a leader. We have to have someone who's our central, our big dog on the school playground here, and Raft will do that. Basically, it does this by each node in our Raft cluster is given a randomized timeout. The first node to reach its randomized timeout will then say, hey, can you guys elect for me? And when that happens, well, he'll generally get elected first because it was the first one to reach the timeout. The leader will then send out regular heartbeats to the cluster and say, hey, like, let's talk about this. Are you still alive? Each time you get that heartbeat, the nodes, the followers or the other nodes, the heartbeats clock will reset. At any given time, a server can be a follower, a candidate, or a leader. And to keep all of our different elections kept in track, we divide this into terms. So basically, one leader or one voting, I don't know what to call that, one election, yeah, there we go. One election is one term. The leader's log is always seen as the source of truth, and Raft is built around keeping the log up to date. So to break it down, say your timeout happens, and you haven't received a heartbeat from the leader, and that's why that happened. So you're going to request others to vote for you. You're going to either become the leader, good for you. Someone else is going to become the leader, all right. Or the vote's going to split. You're going to get a new term. This is all going to happen over again until a new leader is elected. So about that log, say someone is trying to request that they get voted for, but their log is out of date or inconsistent with ours. If that's the case, then we're not going to fall for that. We don't want that game. We want a leader that comes to the same consensus and ideals as us. So Raft is designed around keeping that log up to date. And we will not elect anyone with inconsistent logs. So here you can see up to 6 entries are committed. However, you can see some servers actually don't have all those entries, right? Like those 2. So is that a big deal? Yes and no. The thing is, as long as a majority of the cluster has stuff committed, then it'll persist through crashes, and that means it is committed. I shouldn't use committed before, but we're in too deep. So any committed entry is safe to withstand failures, right? Because it is on a majority of our machines. I cut it off here because there was no good way to end a talk I've already given before. So if you want to see the rest of it, then please go see the talks, or my talk, on different background. All right, so problem solved. We're going to scoot away, my dudes. We're totally chill. Like, that's it. Serf is made. We've added Raft, right? We don't need anything else. No way. Well, here's how I see it. Raft is like a big deal. If you add it to something, you're changing the consistency model of Serf. People might be upset about that. And something I've found when researching this talk and understanding more about HashiCorp is we love to keep things separated so that everyone's happy. This does add complexity when you're trying to trace a bug, but I think for the user side, it's awesome. Also, we're right there at the end, so bear with me. All right, so Consul is bubbles because we decided that Butter or Blossom was the leader and so needed to be Serf. So in Consul, we're all about the service. We're all about that service life. In Serf, we're more focused on our members and our nodes. So let's talk about Consul. Strongly consistent via Raft, we talked about that. We use multiple gossip pools to span data centers, which is cool. We have a key value store and all about that service life, as well as the centralized API and UI people wanted. So let's talk about the key value store. Nope. Vocabulary, yeah. So let's cover some Consul vocabulary. There are still people who work at HashiCorp, not calling anyone out, who don't know the difference between an agent and like client and server, and I didn't know it till like 2 weeks ago, so I don't blame you. So an agent is a process that runs on every machine in a Consul cluster, and it can be either a server or client. I like to think about it as a generic term. A server is a standalone instance that is involved in the Raft quorum. It maintains state. It can communicate across data centers. It's your beefy machines. And then a client, well, dang it. This shouldn't say agent. See, I'm messing it up too. A client is basically, it monitors your application, it runs alongside it, and it's not a part of Raft. It doesn't hold state. It just, if you ever used Kubernetes, I like to think about it as a kubelet, and I feel like I'm going to get a tomato thrown at me for saying that. So service configuration, right? We have our key value store, and this is implemented by a simple in-memory database that's based off of radix trees. And you can go check it out there. But basically, it's stored on Consul servers, but it can be accessed by both clients and servers. And it's strongly consistent because Raft. Network coordinates. So remember we talked about Vivaldi, and we had that picture of him, and he looked really smug? I do. And so when we added Vivaldi into Serf, we did not do much. And it was like very choose your own adventure, have fun. That's not the true story. I think what happened is we added Vivaldi into Serf because it belonged to be in that level, and adding it just into Consul would make things messy, but that's my opinion. Anyways, so in prepared queries, you use them in Consul, and they're basically rules or guidelines for people to follow. So basically, you can use prepared queries to say, hey, if my service fails, explodes, whatever, then use network coordinates to find the nearest two instances or available services, and fail over to those. This makes it really easy for your customers or clients or anything. I always think of it as a website, and if you're rerouting traffic, you always want to do it to the nearest area closest to that traffic. This slide just says, click to add notes. All right, so service discovery, still stored in the same database as the KVs, but it has a different table. And we can use this to basically give Consul services to monitor. And then health checks are very focused on service again, and you can use many different things to build out your health checks. The picture is a build your own. It's a script, I think. Okay. I like this slide too. I like all my slides. So in the beginning, I talked about the IP address problem Armon and I had. It was a really bonding moment, and now we're going to wrap it up. So up top, you'll see that that's an IP address, hard-coded. That was my life before Hashi. Down bottom, with Consul, you can see that we can just call out to Consul, and Consul will dynamically resolve our service for us, which is sick. Also, that wow emoji you can use in the HashiCorp Slack. All right. So Consul today. If you haven't heard about Consul today or yesterday, then that's cool. If you have any questions about service mesh or any of the really scary buzzwords, please find him and go bug him. He loves it. I love you, Paul. All right, so let's summarize. So basically, Consul is all about your service. And it's built upon Serf, which is all about your nodes, right? And memberless, that's just your library that implements Swim. The good way, or a good quote I saw is, Consul can't operate if central servers can't form a quorum, but Serf will continue to function almost under all circumstances. All right, we're going to go really quick. If you like these slides, these drawings, then please go talk to Lookmai. She does stickers. She's great. I love her. Please give her business. This link doesn't work, but if you go to, I don't remember, but I'll have someone tweet it, and please give me feedback. It's a good feedback form. And then finally, if you want to follow me on Twitter, please DM me any questions. Even if it says Nick Jackson, it is totally me. Please send me messages and go to learn.consult. Thank you very much.